Thank you very much. I would like to thank the organizers for inviting me and for the opportunity to hear so many interesting talks. I've got plenty of open problems now in my head. So this talk changed throughout the week as I wanted to show some dependencies of previous talks and remove the intersection. However, I was not able to do it with the talk that just took place an hour ago. So I'm very sorry for the repetitions that will be present. I will be giving a very easy talk on a very classical problem, Plethysm. This is a part of a joint work with Thomas Kalle from Magdeburg, currently at Magdeburg. Please, if you have any questions, feel free to ask. So to show you how easy my talk is, I will start by reminding that irreducible representations correspond to Young diagrams, and I will even say more how one can think about it. Namely, I would like to think about it in terms of Schur functors. So to a Young diagram, I associate a Schur functor. How does it work? I take the space V, if I consider the group SLV. I tensor it as many times as my Young diagram has as many boxes as my Young diagram has, and then I act on the tensor power with the Young symmetrizer. So most of you know Young symmetrizers. Here you can consider them just as a map that takes a tensor, permutes it, and associates certain coefficient and sums up. So for example, for the symmetric power, you just take all possible permutations with coefficient 1, and for the wedge power, you just take also all possible permutations, but the coefficient is equal to the sign of permutation. So as we know, like this, we can get all irreducible representations of SLV varying just the Young diagram. But as we defined it, it really didn't matter that the starting representation was the most trivial one, V. I could have done it for any representation, take the tensor power, act with Young symmetrizer. So in fact, S lambda is a functor from representations to representations. If I apply it to the trivial, just to V, then I get the irreducible representations. But when I start applying it to other, more complicated representations, in general, I get reducible representations, and this is what I call the Plethysm. So application of a Schur functor to another Schur functor. So here I stopped omitting the vector space V, as I usually will not be interested in it. As long as V is sufficiently many-dimensional, the decomposition of such a composition in terms of Young diagrams is just the same. So the most well-known Schur functors are for sure the symmetric and the wedge power. And also in this talk, these are the two Schur functors we will be mostly interested in. So here is an example. We take S4 of S3 in C3, and when we decompose it, such thing with multiplicity 1 appears. So here I mean a Young diagram with 3 rows and 4 boxes in each row. So the first question is, what is it and when did it appear on this conference?
The discriminant in the cubic.
This is the invariant.
Is diagonal invariant.
Yeah. Yes, I mean on Monday we saw this is the degree for invariant for plane cubics. Great. So Bernd Sturmfels gave a very nice talk about invariants, and we see that if we know Plethysm, in particular invariants appear there, and we can recognize them as rectangular shapes. Great. So I hope this is like one of the motivations to understand Plethysms. So if we just focus on symmetric powers of symmetric powers, it means that we are trying to understand polynomials in coefficients of polynomials. So unfortunately, I'm sure that almost every expert in a representation theory has got his own favorite way to compute Plethysms, but there is no really good combinatorial formula. And also many speakers referred to it. There are many formulas how to compute it, but I guess that we are still looking for a really good, really fast one, even for symmetric powers. So the general aim would be to fully understand polynomials in coefficients of polynomials. So here this will be like degree d polynomials in coefficients of degree k polynomials. But we already know this is difficult. This is very, very difficult. So the aim of the talk will be a little bit different, a little bit more modest. So understand low degree polynomials in coefficients of arbitrary polynomials. So I would like to make it very clear. I will be considering small d and arbitrary k. Yes? Any questions at this point? This is my aim. I don't care about complexity, about other things. I really want to understand low degree polynomials in terms for arbitrary inner polynomials. And you might be disappointed. Not much is known about this, even for small d's. But not much doesn't mean nothing. So what is known? So one of the first results is due to Thrall in 1942. He provided a formula for the second symmetric power of nth symmetric power. And it turns out that the multiplicity is always 1 or 0. And it's precisely 1 when your lambda has just 2 rows and both of them are even. So for me, I would interpret these results that Thrall understood quadrics in coefficients of arbitrary polynomials. And you already can see that an important thing that was often referred to during this conference, that the lattice structure plays a role. So it's not only inequalities or polynomials, but the rest modulo some number gives you the result, whether the multiplicity is 0 or not. Here it's very easy, just modulo 2. But later we'll see that such things are quite important. Okay, so we understand quadrics. And of course, when we understand quadrics, what's the next natural question that people try to answer? Cubics. And cubics we also understand. So there are precise, explicit formulas to decompose S3 of Sk. This is not very, very difficult. There are many people who obtained. So this already is later than 1942. There are many different formulas, but in particular there are explicit formulas. I should say that also formulas for S mu Sk, where mu is arbitrary partition of 3, are known. Great. So what about quartics? There is a paper of Howe where he says how he can obtain formulas for quartics. And he also say that interested people can contact him, but he will not put money that the formulas are correct. He just claims that his methods are correct to obtain the formulas. That's something. At least we've got good methods to... Yes, I did. Yes, I did, and he replied... Great. So let's say that quartics can be understood. So what is a problem, you may ask? I mean, how can someone have methods, but he's not like claiming that the result he has is 100% correct? The thing is that these formulas are more and more complicated. And this, I should say, as for Sk, I mean, these are still quite old results. But many different approaches to S mu Sk, when mu is a partition of 3, there are papers after 2000 about that. Great. So the formulas, of course, become more and more complicated.
But there are no negative signs there, right?
I mean, okay. This is not a summation formula. It's an explicit formula. So it's a function in k and lambda, an explicit function. So let's say you take the length of the second row, you add to it k, you divide by 2, you take the floor, and this is the multiplicity.
But do you subtract is the question?
Well, a polynomial has subtractions, but it's a formula. It's a formula. It's a really...
But the question was, do you need to subtract?
No,
Yes.
no, when you write down that thing, like you wrote down S3 something something, like that. Is it like that?
So here the coefficient is like 0 or 1. So this one I would interpret as a function that takes lambda 1 and returns 0 if lambda 1 is odd, and 1 if lambda 1 is even.
I think I did.
This formula, I interpret it as such a function. And the formulas for S3 and S4, they are of such a type. They take, of course, more lambdas. They take, let's say k, and then it's like if lambda 1 is greater than lambda 2 plus lambda 3, and here an explicit coefficient that can have minuses, like lambda 1 minus lambda 2 plus floor of k divided by 2. I mean, this is not the result, but I'm just saying what type of formula one obtains.
So that formula, can it become negative?
No, yeah, I mean, it's a formula for the multiplicity. So when you evaluate it on reasonable lambda and k...
His question is, are there monomials in the formula that have a negative?
Yes. Yes.
I think that's the question.
Yes. But we are not computing combinatorial objects of certain type and subtracting them. So this is not like the usual problem that happens, that you compute certain types of combinatorial objects and you start subtracting them. It's an explicit formula. You are not computing any objects. Okay, so what would be the approach? The approach is as usual and as presented on a previous talk through characters. So you probably didn't forget in 1 hour that characters are symmetric polynomials associated to representations, and that the trace of a representation is a symmetric polynomial in eigenvalues. And for irreducible representations, we've got super important functions that are called Schur polynomials and form a basis of the space of symmetric polynomials. I even prepared an example, but I guess it's very clear by now that if you take just a two-dimensional vector space and if you act with SL2, the character is like this, a complete symmetric polynomial. Yes, this one comes from the action on E1 times E1. This one comes from the action on E1 times E2. This one comes from an action on E2 times E2. Yes? So this is a complete symmetric polynomial. You can easily see that for symmetric powers you will always get a complete symmetric polynomials of this degree. And I will denote it by H. So H for me will be a complete symmetric polynomial. Why are we interested in characters? Because decomposing a representation into irreducible components is just the same as writing the character in terms of Schur polynomials with coefficients, because they form a basis, everything is clear. So what is our aim now? Our aim now is, of course, to understand the character of Plethysm, and later to decompose it in terms of Schur functors. So first, we have to go from the Plethysm that was defined as composition of Schur polynomials to the level of symmetric polynomials. So here the circle will be the Plethysm, and it turns out that of course you can do it on the level of symmetric polynomials. So if your G and F represent Schur polynomials, then this circle will represent their Plethysm, the character of the Plethysm. And this Plethysm has very easy and nice properties, namely in the outer thing, it's an endomorphism of rings of symmetric polynomials. And if the outer thing is just a power sum, so phi n, it's a definition, phi n of x, I just mean sum of xi to nth power. It will be a very important function for me. So if you do not like to compose sure functors, you can consider this as a definition of Plethysm on level of symmetric functions, because any symmetric function can be expressed in those phi's as a ring generated by those psi. And then when you express your outer thing in terms of psi, using the fact that this is an endomorphism of ring of symmetric polynomials, and applying this formula, you can compute arbitrary Plethysms. So some people are nodding, but I'm not sure if it's clear. Yeah, most people are not. Yes, but they do.
Yeah, well, that's
They do.
So isn't the case that this is the point where you just plug in all the terms of C and G? That's the general formula.
Yes. Here you see. Yes.
But that's the general formula.
Yes, but I mean, I prefer to do it this way because for further application. So right now we will just use this proposition. If you would like to know more, I mean, this is like in McDonald's book, very classical. So let's do it for Plethysm. So I repeat the strategy: express the outer thing in psi's, and then use the fact that this is endomorphism of ring of symmetric polynomials. So this is the formula for the character of Plethysm of any S mu and Sk. There are some strange numbers here, and let me explain what are these numbers, using the proof of this thing at the same time. So a few numbers are expressed here. So the sum is over all alphas that divide D, and D alpha is the number of partitions of cycle type alpha. So if you have a partition of permutation, of permutations of cycle type alpha. Yes, so if you have got any permutation, you can decompose it to cycles, and you can ask how many permutations are with the same decomposition to cycles. So this is the alpha, and the proof is very easy. You can see that this is like a two-line proof. The thing is to decompose the character, the sure polynomial, in terms of power signs. So here rho is a partition. Rho is a partition. So rho equals rho 1 up to some rho s. And I define it just to be a product of rho i's. And rho with a number is defined above. So it's just a product of power sums.
And that sum alpha equals rho.
Sorry. In the sum.
Up, above, straight to the left. That.
Yes. There is no alpha here. I'm very sorry for that.
And this phi is a psi. Psi of rho is defined as the product of the psi I. No, what?
This is a polynomial defined there.
This phi is a psi.
This is just a number. This is just a number. And I'm now going to explain this, because I didn't say what is this. Yes? I didn't say. So recall that partitions label not only representations of the symmetric linear group, they also correspond to representations of the complete symmetric group. And complete symmetric group also have characters. And by psi mu, I mean the character of the representation associated to mu of an SD representation. And now I can evaluate it on a partition that represents a permutation, because a partition represents a permutation up to conjugation, because it defines the cycle type. Also, some people are nodding, but I think that not all people. Maybe there are some questions. So just to sum up, this is a formula to express the sure polynomials in terms of products of power sums with coefficients that are just numbers that we can understand and compute. Dot. And now, using the fact that the Plethysm is just an endomorphism of rings in the outer thing, we can put it and compose it with the character of the symmetric power, which is just the complete symmetric polynomial as we have seen, and we obtain this easy formula.
What is D alpha now?
d alpha is a number of permutations of a given cycle type. You can write a precise formula, but I think it's easier to just remember that it's a number of certain permutations.
Basically, Schur-Weyl duality, right?
Yes, you can derive it from Schur-Weyl duality. Yes, you can do that. Although I always did it on polynomials. Great. So at this point, when I think I learned it from Laurent, I thought the game is over for Plethysm. We know the character, so we know the polynomial. What's the problem? I mean, we just reduced a very complicated problem to a problem in linear algebra. We have to understand this polynomial as a linear combination of Schur polynomials. And the problem is, I think, more or less the same as in Professor Popov's lecture. Linear algebra, when you are doing it in coefficients of polynomials, becomes hard because there are so many of things. So this is the reason why this problem is not completely solved. I mean, you can try to do it like combinatorically or using linear algebra, but the formulas become complicated, the computations become more and more complicated. But we still have our aim. We really want to understand low-degree polynomials in arbitrary polynomials. So we don't care if it becomes complicated. We have to do it. So what can we do? So I think there are two things in general that one can do in such a case. Either really aim to really obtain the aim using some new methods that people before us didn't use, or try to ask a different question. Maybe not an explicit answer, but something connected to the answer. And I will present both of these approaches, point 1 and point 2. So point 1, we have to use some new methods that people before us didn't have. So guess what will be the methods that people in the 80s didn't have? Well, the first problem is to understand this polynomial. Psi rho hk. I don't know if you see what it is. This is just a product of complete symmetric polynomials. So first of all, this is a product of psi rho I hk, because I told you that the Plethysm is an endomorphism in the outer function. So we would like to understand this, but this is just hk of x to rho I, a complete symmetric polynomial of degree k in coefficients that are not variables, but powers of variables. So what are the coefficients of this coefficients? And we have a product of such things. How can we understand the coefficient? Well, let us translate it to a purely combinatorial problem, as a few speakers before me did. So you can immediately see that the coefficients of this polynomial are governed by the following combinatorial object. You take a matrix. Your matrix has got certain weights. And so the entries will be xij. And you want the row sums to be equal to k, to a given fixed number. And you want...
So xij are numbers.
Yes, numbers. We will be counting number of matrices with non-negative integral entries, with rows summing up to a given number, and weighted column sums. equal to lambdas.
We should write kj.
No, the k is the same everywhere.
It's HK.
Oh,
It's hk.
I see. Okay. Right.
So this sort of tells me which monomials I choose in each of the product. Very, very easy translation.
I think
So this expresses.
there.
Oh,
First one is the row of columns and a fixed row, so that's sum over j, and the next one is sum over I.
well, that depends how you number them. Here I gave I and here I gave j. Sorry, probably many mathematicians.
So this is the arithmetic of the degree.
Yes. I just encode the coefficients. Very simple. But the good thing is that now we can apply new methods that people didn't have in the 80s. Namely, this is a perfect job for a computer. Because this is a polytope. This is a polytope, and there are new algorithms. People developed new algorithms to compute such things. In particular, there's a Barvinok program, which greatly solves the problem of computing parametrically, the number of points in a cone. So I had a few questions about the Barvinok program because it was mentioned during a few talks. We use it through ISL library. It's still under construction, but it works already very, very well. So what does Barvinok? We have a polyhedral cone. So this is a three-dimensional polyhedral cone. And this is and we have a projection. So I will be projecting it to a two-dimensional space. And this is the input. And the output is a counting function of fibers. So I would like to know what is the cardinality of a fiber above a given point. But I don't want a number. I want it as a function. So what do I get? Notice that this ray projects here. And of course I get a different function on this piece and a different function on this piece because the facets supporting the cones are different. Yes? So I get a quasi-polynomial here and a quasi-polynomial here. What I mean by a quasi-polynomial? I mean just a polynomial, but the coefficients depend on parameters modulo a fixed number. And this is the output of a Barvinok. He gives you the chamber decomposition and he gives you the quasi-polynomial in each chamber. Just to check if the audience is with me, what would I get if I would project it to a line? So this polytope projects to a point, and I'm counting the cardinality of a fiber. Yes, someone is with me. Great. Okay, so I project it to the line, and I assume that there is a polytope at height 1, and then there is a dilation of this polytope at height 2. So, in fact, the projection function counts the number of integral points inside the dilations of the polytope. And this is, I mean, depending if this is rational or integral, this is either a polytope or quasi-polytope. The Earhart-Hilbert polytope.
Whether it's a polynomial.
Yes, whether it's a polynomial or quasi-polynomial depends if this is integral or rational. Great. So we obtain a lot of cones. We have to project them. So I cheated here a little bit because I told you how to understand the coefficients of the character of the Plethysm, but coefficients are not enough to understand it as a decomposition of Schur functors, but there is a standard trick that was mentioned during the previous talk and many other talks. You can call it in many different ways a finite difference operator. It amounts to multiplying your polynomial by the discriminant and then looking for the particular coefficient there. Also a job that the computer does very, very well for you. And we get explicit answers where mu is any partition of 4 or 5. So in particular, we also obtain explicit answer for S mu of wedge K. Of course, don't try to implement it as I did it in the talk because the computer will break, but after a few tricks, you can do it without problems.
But computer will only do for a fixed K, right?
No, for any K. A formula for any K. So I should mention there are 1,000 programs, and the best one is Lee, to compute Plethysm for fixed mu and fixed inner thing. But we don't want that. We treat K as a parameter in everything we do. It's a parameter. And our formulas are completely explicit. So we obtain a decomposition of the space of K's and lambdas, the domain, a finite decomposition into chambers, and in each chamber you get a quasi-polynomial explicitly given by the computer. So this is what this is what I just said. Yes, so we have a space in the domain is K lambda. You don't need both, but let's say we have both. And then you have a chamber decomposition, and in each chamber you get an explicit quasi-polynomial that gives you the answer to your problem. So if you would like to then know, I will pass later what you can explicitly do with that.
Huge.
Sorry?
The number of chambers would be huge.
Not really that huge. We've got numerics. It's like
As mu grows, of course.
But mu is at the most 4 or 5.
I know, so that's what makes
yes. That what keeps it still reasonable. I guess like 120. I don't remember.
That's all.
Sorry?
That's all. Around 100.
Yeah. Not. I mean, it's that many that you can look at it being as a human being, although you are not supposed to do that.
I mean, the decomposition of 75 of 75 is already...
Yes, because they are writing it explicitly, not as a formula. But we've got S5 of SK for any K. Any K.
Mateusz,
As a function in K.
for example, for me, partition of 4, how many chambers do you get?
I have to check in my... we have.
I mean, 5, 100.
I guess something between.
You use projection once or many times?
Sorry? Oh, many times. Number of mu boxes factorial. And I didn't show you any chamber decomposition because for quadrics there was no chamber decomposition. But already for cubics you need this chamber decomposition. So there is a different formula depending on inequalities. And of course there is a different formula, this is a quasi-polynomial, depending on rest modulo a fixed number.
So if one doesn't care how you got the formula, there is a precise formula for the composition up till S5.
Yes.
Is that what you're saying?
Yes. Yes. Even S mu, where mu is any partition of 5. S5 of SK, there is a formula in K. So not even for fixed K, parametric in K. So we understand quintics of any polynomials.
So is this formula not a K?
No.
What you compute now, I think, as I mentioned, grade spaces, you still have to do something to find out.
Yes, so this is this trick that was mentioned by, it was called sure something. I mean, you multiply by the discriminant and you look, but we do this, of course. We are not computing weights, we are really computing multiplicities, we are not cheating.
Another step that you...
Yes, that I didn't talk about.
You also have to do that.
Yes, we did that. Yes.
One has to do that.
Okay, but this is only half of what we did. I told you that there is a second point. You can try to understand things not explicitly, but for example, the asymptotics. So I already told you that this thing is a piecewise quasi-polynomial for fixed mu in K and lambdas. So for me, there is a very natural question. What's the leading term of this quasi-polynomial? Can we understand it? And when you are doing combinatorics, you immediately see that there is the candidate for the leading term. And you are sure that this is your leading term. And then you start looking in the literature and you find that people before you also identified this leading term, and they also were sure that this is the leading term, but it seems no one really proved it. So Howe conjectured it in the 80s. I contacted like 15 experts, I guess, and Al-R is Littlewood Richardson. That's a big name. It's really coming from Pierre's rule here. Yeah, so more or less, if you want to understand lambda in S mu Sn, you should understand lambda inside Sn tensor, the weight of mu. This is much easier, because this is just...
It's the number of fillings of a tableau with
Yes, but in this case it's like even easier, because it comes from Pierre's, because it's a symmetric power.
It's a constant number. It's the number of fillings of a tableau
Yes.
with a given weight.
Yes, I call it the Pierre's rule. Yes, but it is, yes, this number. But anyway, yes, we know how to compute this. Yes? Well, at least the leading term. It's connected to the volume of the polytope. And then, if you want to understand the multiplicity here, just multiply by this number. Dimension of mu is the dimension of mu as a representation of the symmetric group. Okay. This should be, I guess, many experts probably should feel that this is obvious. L-R is from Littlewood Richardson, by which I mean the term in the tensor product. So what's the multiplicity in the tensor product?
Of what? Which lambda? LR of lambda in there?
Yeah.
Yeah, correct.
Yeah. So
And what was D now?
D is mu.
Oh, size of mu.
Yes. So, for example, for symmetric power, I mean, imagine that this is just the symmetric power. So that this is just D. Well, what's the difference between a tensor product and the symmetric power? If you take an arbitrary tensor, if you symmetrize it, more or less 1 over d factorial things will fall here. And if your partition is just one row, then this is just the trivial representation that has dimension 1. So you see that this is very intuitive. So we also prove it. And I will be very happy to discuss with experts, because maybe I still believe that there should be a very easy, not combinatorial, but a representation theoretic proof of that. So conclusions and future plans. There was a talk by Mateusz. So what's the difference with the talk by Mateusz? He was changing the degree, keeping the inner functor fixed. So he had like one variety and changed the degree of polynomials. I'm doing the other thing round. So I'm changing the variety, I'm changing the polynomials, but I'm keeping the degree. So after talking to Laurent and other people, it seems that this question mark should be a dot. So from combinatorial formulas, it's very clear that this should be a quasi-polynomial for large K. But it seems that it's a quasi-polynomial just from the start. So it means that you can understand the Plethysm just by understanding it asymptotically for very large values of K. Because the quasi-polynomial is determined by finitely many values. So if you are able to understand it for large K, you can deduce the quasi-polynomial and understand it for small k. So I hope this will be a work in progress with Laurent.
That's a theorem? Oh, no, that's a question mark. I see. Okay.
Well, Laurent and Mateusz made it a theorem already, I think. So if you are interested in the explicit decompositions of S5 or S4 of Sn, this is the web page we set out for it. If you really want to see the formulas. I should say that these formulas, you can do much more than just asking for a multiplicity for given k and lambda. You can evaluate it symbolically. So for example, you can test your conjecture. What's the multiplicity when the row of the second, when the second row in your diagram equals the third one? So you just input lambda 2 equal to lambda 3 in our formulas and the computer does it for you. If you are lucky, the formula simplifies a lot and confirms or contradicts your conjecture. And then how fast is the evaluation of an explicit formula? So here is an example. If you would like to know what's the multiplicity of such a random Young diagram inside such a Plethysm, it's this. And you are not supposed to see it, but the evaluation of such a formula, it takes under 1 second. And Thomas says that we can do it when these numbers would have millions of digits. So explicit formula is like really fast. No, there is no mathematics there. It's just showing that we can do it for really arbitrary numbers, evaluate the formula.
Up till S5 or even beyond.
So we've got formulas up to S5. If you would be interested in S6, we can probably push it. Well, there are a few tricks. We reduce a number of variables. We use the Barvinok. Even such things as an ordering of summation played a big role in the computation. So we have sums, and of course they are commutative. But choosing the right order in the summation, somehow the result depended on that.
I cannot compute. There is a big LCM between the parts of lambda.
Sorry?
Big gap.
LCM.
Is
The parts of lambda. Is lambda a multiple of some small...
The numbers were random. It's 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. It's random in binary representation.
The first one, what's that one?
The first one is so that it makes sense. I mean, the total weight has to be equal to 5 times 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Because otherwise it's 0. That wouldn't be interesting. Yes, that one. So I planned also to tell you what are the weak points of our algorithm, but I guess I don't have time. I have time? I can tell you.
Let's get the weak points.
So there are a few very weak points of our algorithm. So this computer expert, so first of all, why this ISL library works so well? Because when you have loops in your program, for loops, this is like a parametrization of some geometric object in a high-dimensional space. And they want to optimize for loops very well, so they want to have a better parametrization of this object. So they really worked hard to make these algorithms nice. But the things with algorithms and parametrizations inside them is that these formulas were never meant to be seen by human beings. But they've got a thing that transforms the computer formula into a human readable output and read it back in. But it's very, very bad. They are working now on it, and they are not very much interested. So our formulas are in human readable output. But when you feed the computer our formula into the computer, because this reading function is so bad, this takes time. Just to read the formula. I mean, it's not a huge formula, it's a few pages, so you can look at it being a human being. And once it's read in your memory, computer can add it, subtract it, do anything with it, like in fractions of a second. But they just didn't pay attention into the reading thing. So if you just want to do one evaluation, it may take long, because reading in our formula takes long. And another thing is, we already know that our formula is a formula, it's not the formula. And the problem is that a function, for example, constantly equal to 2, you can present it as a function that is 2 for x greater or equal to 0, and x plus 1 square minus x square minus 2x plus 1 for x less than 0. I mean, you can do it. And the problem is that the computer cannot always join and say, oh, this is the same as this. So the computer doesn't care, because evaluating this one and evaluating this one is very easy for him. But a human being would care to have like sort of a minimal representation. And I hope to be able to present it maybe in a year. What is, for example, the minimal chamber decomposition for arbitrary Plethysms?
Yeah. So you can, for example, if you have these two chambers, these two formulas, you can just plug in random numbers and check if those are the same. Just plug in random numbers from these two chambers and just see for random numbers are those the same.
Yeah, he certainly has method.
Yes. So for sure there would be like a good post-processing thing, but the thing is that probably it will still not fit on one page. Maybe you will be able to reduce it to 2 pages. So probably JM also wouldn't be happy to look at it. And for computer it sort of doesn't matter. Anyway, he evaluates it in 1/10 of a second. But certainly we could do better. Thank you.
Yes, this is, I mean, when it is yes, this is a quasi-polynomial. Yes, of course.